Hello, people at home. Hi, Nicole. Okay, let's think. I need to talk about this. Talk about that. And then I need to talk about this. Okay, so we've seen these kind of representations of molecules that are the wedge and hatch lines that would describe something tetrahedral. We've seen them written just as Kekule structures. We've seen them written as Newman projections. Time to turn this, which we have shown as a hexagon with either the wedges pointing out towards you or away from you, and we've seen as a chair or a boat, time to turn this into a Newman projection also. So to do that, what you have to do is find the parallel bonds and look straight down them so that they go away. Now, what I've got here is an atom with that Y shape coming towards it, and immediately behind it is another atom that we can't see, but you can see its bonds radiating away. So we can draw a Newman projection for this set. And we can see that it's staggered, that there's nothing behind this. This is the chair, staggered. And we can do it for the other one as well. Draw a Newman projection here. So what we're going to do, we're going to draw a Newman projection of this and a Newman projection of that, and then just tack them together by having a bridge that comes over the top and the bottom. This is a chair, and if I flip it into a boat, now everything is eclipsed. Everything is eclipsed. And if I flip that into the other chair, now everything's staggered again, only now the bridge is up top at the back instead of being up top at the front. Okay? Let's draw that. Actually, I'm going to move that a little bit. So here's what we do. This is an eyeball. It represents our path of vision. We are going to look at this molecule straight down that bond. These bonds are parallel to each other. They're the two that are in the middle. We're going to look straight down them so I can see the front of this and I can see the staggered atoms behind it. This and that are just going to be tacked on as a bridge. Okay, doing it this way, we have to pick. Is this going to be the Y-shaped thing because the bridge is up top, or is it going to be the inverted Y? Wait, didn't do it. The inverted Y. Okay, so let's do it that way because this is up top. So this is going to be a Y shape. There's a set of atoms here in a bond that is parallel to a set of atoms here. This CH2 that's pointing up is up and between these parallel bonds, so it's this. We're not concerned with its shape. It's just acting as the bridge. Okay, now put everything else in. There's a hydrogen here, and a hydrogen here, and a hydrogen here, and a hydrogen here. That's how you draw a Newman projection of a cyclohexane. People at home, you all good with that? Okay, all right. I'll give you a second to draw that. And we'll move on to the next one. That was this. To turn this chair into a boat, I'm going to flip that back, apex up. Again, so the front part of my molecule didn't change. The ring flip doesn't affect the front part, just affected the back part. But now everything is eclipsed. Go ahead.
By that projection, is that not from our perspective from here, it's from the sideways perspective?
I'm not sure I understand what you're saying, so I'm going to answer the question that's in my head.
Okay.
To change this into this, I have looked down that bond, which is this bond right here. So I have lined it up with my eye so that I cannot see the atom that is behind it. Cannot see the atom that is behind it. If we wanted to give these numbers, let's call that one number 1. Where in my diagram is that? That one? Okay. This is in front of number 1. In front of, in this perspective, when you turn it around, it's going to mean to the right of. So that gets to be number 2. Where's number 3? This is number 3. Where is number 3? That's 3. 3 is hidden behind number 2. Five is at the back, and 6 is up front. Write the numbers in if it helps. If it's not helping, don't write them in. Okay, that's how learning works. You do the things that help you, and you don't do the things that are holding you back. If you're self-aware enough to know the difference. Okay, from the chair, how can I tell it's a chair? Because it's staggered into the boat. And again, so his boat sideways. So now, my point of view, to turn this is my eyeball. I'm going to look straight down the middle of this. So my Newman projection from this side-on boat is straight down those bars. See this? Behind it is eclipsed. I see this, behind it is eclipsed. I see this bridge, behind it is another bridge. Here's where I start. That's the front 3 atoms. That one, this one, and that one. That one, this one, and that one. In this case, in the case of a boat, everything is eclipsed. And this kind of leads us to understand why this is not the best. That's a higher energy conformation because of all of those repulsions. And there are people out there measuring that, and in fact, it depends which university you go to. Some universities, when we talk about the conformational analysis, they don't just say best, middle, worst. They put numbers to it, and they actually make you calculate the numbers. Hold on. Okay. If you start throwing substituents on this, you just figure out to avoid having them be next to each other, try and put them as far apart from each other as you possibly can. Okay? More on that later, because this week's lab exercise is all about conformation and sketching, so there'll be more. Okay. So what we've seen in chairs and boats, those are conformers, conformational isomers. They are different from each other because they have different energies. The molecules reward the chairs by allowing them to dwell longer in that conformation than the boats because they're lower in energy. There are other isomers. So let's see what we know. We know configurational. Take an atom off the molecule, move it around and stick it back on somewhere else. That is a change in configuration. Configurational isomers are also called constitutional isomers or structural isomers. We've done them. We know that. It's the difference between 2-bromopentane and 3-bromopentane. Same formula, same family, different positions of the bromines means different polarity in that molecule. So it has a different boiling point. It might have a different application. Conformational. Conformational, we've done. And we've done it with chain molecules, and we've done it with ring molecules. Optical, we haven't done optical yet. Can do start optical isomers today, and optical isomers will be next week's lab activity. And then there's geometric, and we haven't seen geometric yet. On purpose. We've seen molecules on the board that had the potential to be geometric isomers, but I showed them, we talked about the configuration, and then they were erased from the board before anybody could say, hold on a minute, I think I can see something. Okay, so I'm going to come back to that. Let's talk about these. Have you all heard of Louis Pasteur? Pasteur, famous, gave us, what did Louis Pasteur give us?
Oh, pasteurization.
Yeah, he gave us a safe milk supply, I guess. Yeah, so he was very, very active and is responsible for some advancements that still have use today in the world of germs and biochemistry. But he also did some important chemistry. Now, have you ever, you know what refractive index is? You do, you just don't know it's called that. Have you ever been to a lake or a pond and you put a stick in the water and you notice that it looks like the stick bends, right? It's because the medium of the atmosphere and the medium of the water don't share the same refractive index. So the light travels differently and is refracted, it is bent. Imagine a world where if I go to your pond and I stick my stick in your pond, my stick appears to bend to the left. But if you come over to my pond and you stick the stick in my pond bends to the right. Louis Pasteur made crystals of tartaric acid. And they were nice, big, white crystals. And he noticed when he looked at them closely that some of them leaned to the left and some of them leaned to the right. And he thought, well, they're just leaning. But then when he tried to line them up, the shapes of the crystals didn't line up. So he separated them into two piles. And then he dissolved them into water. And he pushed a beam of light through them separately. And the light passes through one of the samples and turns left. And the light passes through the other sample and is refracted right. And if he took them both and mixed them together, then the light passed straight through the middle. There are isomers hiding in plain sight. We can't see them because we haven't trained our eyes to see them, but they're called optical isomers because they have a physical outcome. They bend light either to the right or to the left. So optical isomers can be plus or minus. If you are the plus isomer, you bend polarized light to the right. And if you are the minus isomer, you bend, oh, I missed a word, polarized light to the left. Let me give you an example of a molecule that displays this behavior. Two butanol. Oh, displays this behavior. Why am I not showing on the big screen? Not that it matters. Okay, so everybody needs to sketch 2-butanol. After you've sketched it, start making it with your little plastic kits. So people playing at home, the people in the room all have an individual model kit, and they're all going to make me a molecule of 2-butanol, and we're going to mix and match and see what we've got. Because a random sample of 7 people in class should be good enough. Use 4 carbons. Actually, I'm not going to do the work. People at home. I've got, oh, that's not what I wanted to do. I've got the people in the room working for me doing something else. You can go ahead and draw the structure of 2-butanol. Draw 2-butanol as a Kekule structure for me. We've got somebody going straight for the zigzag. That's great. Okay. Now, somebody else off to the side of that. Draw it as the Kekule structure. Show me all the bonds. Somebody has a tablet that didn't do that with a mouse.
Yeah.
Put the hydrogens on. Put the hydrogens on your molecule.
Hydrogens,
Yeah, little white ones.
little white ones?
Yeah. Oh, you got.
Probably one.
Yeah. Mm-hmm. Oxygen is red. Carbon is black or gray. Hydrogen is white. All right, people at home, you look like you've stalled. Carbon is either black or charcoal gray. Oxygen is red. Nitrogen is blue. We don't need any nitrogen. The halogens are green. We don't need any of them. Sulfur is yellow. If you've got sulfur in your molecule, you're way off. Okay, so yeah, that's yeah, okay. Molecules are starting to come in. When you're done, oh.
What?
Because these are tetrahedral.
Oh,
Who's got one that's almost finished? That looks like it's finished.
Yeah, ish.
And then this one is. Okay. I'm going to take the low pins off. So you'll get it. Okay, so two different people gave me two versions of this molecule. 2-butanol. 1, 2, 3, 4. 4 carbons. But, meth, ethyl, pro, but, anol at the 2. So the zigzag tells us this, but what it doesn't show is all the hydrogens and all the atom labels. So the Kekulé structure is marginally better, because what we're about to show you is hidden. Because 2-butanol is one of those chemicals that if you call up the chemical manufacturer and say, I would like a liter of 2-butanol, they say, certainly. Which type? Which one? And you go, hold on a minute. There's only one type of 2-butanol. There's only one type of 2-butanol. And they say, I assure you, sir, we stock more than one type of 2-butanol. This is somebody from the audience's representation of 2-butanol. It's tetrahedral carbon. At the 1, there's a tetrahedral carbon. At the 2, it's tetrahedral carbon at the 3, and a tetrahedral carbon at the 4. This is somebody else's representation, picked at random. Tetrahedral carbonate 1, tetrahedral carbonate 2, tetrahedral carbonate 3, missing a hydrogen. Did it fall off?
No, I took the lone pairs.
No, I took the lone pairs off the oxygens.
Is that mine?
I don't know.
You can have another one.
I need,
Now, this molecule. Is it the same as that molecule?
Looks to be it. Yeah.
This molecule, that molecule. Are they the same? The way to know that molecules are the same is to take them both and superimpose them. Like if you took a photograph of this, remember overhead projectors? Remember those? If you took a photo of it and you put it on an overhead projector slide, and then you took a photograph of this and put it on an overhead projector slide, when they overlap, do they match? And the answer here is yes, they do. So two people made the same molecule. They made the same isomer of the same molecule, but that's random. A third molecule just entered the game. This molecule, 2-butanol. This molecule, 2-butanol. Are they the same as each other? If I try to make these things line up, oh, those carbons are not tetrahedral. So it has to go back. See that? That's not tetrahedral. That atom has to go. That atom's bigger than these other atoms.
Oh, yeah.
Yeah, they shouldn't have put a black one in the box with the other black ones. Okay, we're almost there. People staying at home, stay with me. Stay with me. Okay. This is 2-butanol. This is 2-butanol. Are they the same as each other? If I line the carbons up, these oxygens line up in the wrong place. So I'll go ahead and line those oxygens up in the correct place. And now the carbons line up in the wrong place. These are different from one another. But that's not feasible when you deal in 2 dimensions. They only become apparent when you deal in 3 dimensions. These have been with us forever, since the dawn of time on this planet. And Louis Pasteur was the first person to notice that these are different from each other. And he didn't know about three-dimensional structure. It came later. He didn't know bond theory and three-dimensional shape. That came later. That's how difficult this one was to spot. These are not the same as each other. Now this and this get to be special because of that carbon. They're not special because of this carbon. They're not special because of that carbon. They're not special because of this one. This one is special. It's what we call a chirality center. And that chirality center exists because it's a tetrahedron and it has a hydrogen, a methyl, an ethyl, and an oxygen. It has 4 different groups. And when you have 4 different groups around a tetrahedron, three dimensions, you have the potential to mess that up. Now, what this and this do have is, let me find the right way of doing it. They're mirror images. This molecule and that molecule are mirror images of each other, but they are non-superimposable. When I try to make this line up with that one, it doesn't work. Okay? This hand is the mirror image of that hand. The pinkies are the furthest. If there's a mirror in the middle, the pinkies are the furthest thing away, the thumbs are the closest. And you think, well, no, look, they line up. Well, you're doing it wrong. You're doing face to face. To truly line up, my thumbs are on the wrong way. And when you try and make the thumbs line up, now the other thing's wrong. Okay? So what we're looking at here is that. This is a chirality center. And a chirality center generates optical isomers. Chirality centers generate optical isomers. Those optical isomers are now going to be called enantiomers. And enantiomers are non-superimposable mirror images. So this is the universal sign for a mirror. It is a straight line with a diagonal hatch. On this side, I'm going to draw a tetrahedral carbon that has 4 different bonds attached to it. On this side, I'm going to draw a tetrahedral carbon that is the mirror image of the other tetrahedral carbon. Furthest away from the mirror, these. Closest to the mirror, those. Okay, so my 2-butanol had a hydrogen, it had an alcohol group, it had an ethyl, and it had a metal. One of these isomers is the plus isomer. One of these isomers is the minus isomer. I can only tell which one is plus or minus if I do the experiment. I cannot look at this shape and say, that's the plus. I can only find out which one is which by doing the experiments in an instrument we call a polarimeter. And we have a couple of those, and we'll do that in lab next week. What we do in the meantime, before we identify which one is the plus and which one is the minus, we're going to give these names because one of them is a left and one of them is a right. One of these is a left and one of them is a right. So what we're going to do instead is name their configuration, because deep down, these are configurational isomers. Right? These are mirror images of one another, but they don't overlap. If I want to make this one and that one overlap, here's what I have to do. Come and hold this just on camera. You don't have to be on camera, but just hold it on camera to know that I'm not faking it, right? This isn't a magic trick. Just hold it right where it is. There you go. You're not even on camera. In order for me to make this one match that one, I have to move the position of atoms. And now they match. That's a configuration. These two configurations were hiding, and we couldn't see it. They're just hiding in plain sight because we hadn't grown up to think in 3 dimensions yet. We were still only thinking in 2 dimensions. So I'm going to name this as either a right or a left based on its configuration. That does not mean that I know if it's really a right or a left, a plus or a minus. And here's how I'm going to do it. I'm going to prioritize the substituents. Going to prioritize the substituents in descending order of atomic mass. It's not done. only of the atom directly attached to the chirality center. So the very first thing that I have to do when thinking about a chiral molecule is to identify the carbon that has 4 different bonds. Sketch it out, and then we're going to number them in descending order. That's my chirality center. The atoms that are directly attached to it are oxygen, hydrogen, carbon, and carbon. What's the atomic mass of oxygen? What's the atomic mass of hydrogen? What's the atomic mass of carbon? Well,
Wrong one.
what's the atomic mass of carbon? I've tied. These two are the same. If there's a tie, look at the next atom. This carbon is bonded to hydrogens, and hydrogens have a mass of 1. This carbon is bonded to another carbon, and that carbon has a mass of 12. This gets to be number 1. This gets to be number 2. This gets to be number 3. And the hydrogen gets to be number 4. Alcohol is number 1. Ethyl is number 2. Methyl is number 3. Hydrogen is number 4. My naming convention says prioritize the substituents in order of descending atomic mass of the atom directly attached to the chirality center. Done it. In the event of a tie, look to the next atom. Done it. With the bond of lowest priority pointing away from you, the bond of lowest priority is the one that goes to number 4. With the bond of lowest priority pointing away from you, count those. 1 to 2 to 3, 1 to 2 to 3. If it goes clockwise, you have the R isomer. If it goes counterclockwise, you have the left-handed, the sinister isomer. This right here goes 1 to 2 to 3. This, counterclockwise, is S2 butanol. This one goes 1 to 2 to 3, that is clockwise. This one is R2 butanol. People at home, this is quite a new thing, but it's going to be a very big deal for us. You okay with it? We'll do more. Don't worry, we're not just doing this once. There will be a lot more. Okay, see you all on Wednesday. Let me know if there's anything you need between now and then. This week's lab activity is a modeling activity. It's not a wet chemical activity. We're going to use some software and some plastic models. There is an advantage to coming to class, but it's okay if you don't.
Good question. Yes.
Yeah, I think by the time Friday rolls around, we'll have, yeah, I think we'll have material. Now, I am fully aware of the complication that having some people opt to take a test in person has with the same set of people, their classmates, taking that same test at home online. That will not be the case. The exam will be 100% online, and it will be a mixture of a timed multiple choice test plus a worksheet in which you have to do some sketching and have to turn it in. Okay. It'll be a hybrid test. It'll be partly timed test, part worksheet.
Either way, you're still going to take it online.
Yeah, there'll be a submission link for the worksheet, and there will be an online quiz for the actual test. Yeah.
So are we coming in on Friday, or are we just gonna stay at a?
So that means we can actually use Friday as a lecture, because I can give you the whole weekend to take the test. I don't particularly care.
Well, like Friday, just come in and be like
Just normal class?
normal class, but like review.
We depending on how desperate I am about being behind, which I'm not particularly concerned about, we could learn something new, plus we can answer questions. Answering student questions is the best use of our class time.
Like that?
But not, so there are no dumb questions before the test. I'm teaching another class, and I had a student over the weekend say, I can't take the test. It's not letting me in. There's something wrong with the browser. And so I complained to the people who had the browser, and they said, they reminded me that the test only opened today. So the person couldn't take the test because the test wasn't open, but complained anyway. So there are dumb questions before the test. But no, there are no dumb questions before the test. Or the person that complained this morning, I've been locked out of these 2 quizzes. And I looked and like, well, no, one of them closes next weekend, and then one of them closes the weekend after. You are not locked out. You have no concept of calendar.
Yeah.
But yeah, if we use the time to field student-generated questions, that's the best use of our time. Becca's got lots of questions.
You know, I didn't do by the end of the weekend.
So that's special.
Brian, probably. I'm leaning that way.
homework with you tomorrow?
Yeah. All right, I'm gonna close it up.
No, it's like